Welcome back. In this section, we're going to look at how we can measure the rate of reaction on a concentration time graph. A part of knowing that a reaction has taken place is that there is some kind of chemical change, which is indicated to us by some kind of change in physical appearance or some other characteristic of the chemical. If we want to know how much of the reaction has happened, if we want to know exactly where we are in the reaction itself, then there are a number of indicators that we can rely on, and it all depends on the kind of reaction that is occurring. For example, if it's a reaction between acids and bases, anything that might change the pH, then we could actively monitor the pH of the solution. So we could do that with a pH meter, or alternatively, we could do it through a titration, looking exactly using an indicator, the point where something has neutralized, for example. If the reaction is gas producing, then we could measure the volume of gas as a function of time. We could also look at how the reactants get used up, how the mass of the sample in the conical flask decreases with time as the reaction takes place. There might be changes that change the appearance of the chemical, like the forming of a precipitate blocking out the X that is underneath the conical flask, or indeed we could be looking for a colour change. Now with that final one, looking for a colour change, we can actually use this, a colorimeter. And what this does is that it basically looks for colour changes in a solution. So you take your chemical and you put it into this thing called a curvette here, and it's basically like a square-sided little tiny test tube or vial, and you place that inside this device, and it shines a light through it and then monitors the transmission of that light to the other side. Let's look at that in more detail. So inside the colorimeter, what is occurring? Well, first of all, there is a light source, and it tends to be nowadays that it's of a single wavelength, but in times gone by it would have been a light bulb which would have been filtered down to produce monochromatic light. So basically all of the other wavelengths apart from the one we're interested in would get absorbed, allowing the transmission only of one wavelength of light, one colour of light. Now what would happen to that light is it would be allowed to go through the curvette containing the chemical. And as that chemical undergoes a chemical reaction and its colour change, you could monitor the amount of transmitted light that is being detected on the other side of the curvette by a photocell or an LDR, and then output that so that you can actively track what is the transmission of the light, an indicator of how much reaction has occurred, and even an indicator of the concentration of either the reactants or the products. So here's a nice example of a reaction that you could track with a colorimeter. It's a reaction between bromine and formic acid, which we now know as methanoic acid. So what happens here is we've got bromine, this diatomic molecule, and we mix it with this, it's basically carbon, it's got a double bond to one oxygen, single bond to another oxygen with a couple of hydrogens thrown in. And what happens is the electrons from the bond of the bromine go across to help form a double bond between the carbon and one oxygen and the carbon and another oxygen of CO2. In the process, we get a load of ions produced, a load of hydrogen ions and a pair of bromide ions. Now, when that happens, when bromine breaks down to bromide, then you get a decoloration. The bromine is providing the dark reddy brown sort of colour, and that slowly goes away as this reaction takes place. If you put this into a colorimeter, what you would see is the amount of transmitted light would increase if you picked a particular wavelength of light that corresponded to the colour of bromine. Another good reaction that you could put in a colorimeter is the decomposition of sulfuryl chloride. Now this is not one you would actually want to do because sulfuryl chloride is not a very nice chemical. So sulfuryl chloride is sulfur dichloride dioxide, so one sulfur, two oxygens and two chlorine atoms. And what happens is at room temperature it is a clear liquid with a boiling point of about 69 degrees. If it gets warmer than that, it turns into a gas and starts to decompose. It starts to break up into smaller molecules, forming sulfur dioxide, which is pretty unpleasant, and chlorine gas, which is also pretty unpleasant. But that chlorine gas is green, so we could observe the concentration of this product being formed by looking at how green it is. We could also look at just how much of the sulfuryl chloride therefore must have disappeared as a function of time. So here we've got some pretend data, and this pretend data comes from an experiment where basically the amount of sulfuryl chloride has decreased as a function of time. And I want to show you how we can process this data. So here is a graph of some concentration data. So I'm plotting here on the y-axis the concentration of the sulfuryl chloride. This is the concentration of the reactants. It's going down as they're used up in this reaction. But what is the rate of reaction? Well, we've got time on the x-axis here, and you can see that I've compiled that in Desmos by basically putting the time and by basically also putting the concentration. Now, the first thing I wanted Desmos to tell me was what was the best fit curve to this data. Now, it's obviously an exponential curve, a power law, and so what I've done is I've used this and I put B in as the coefficient, and it is going to tell me what the best fit to the data is, what value of B best fits. And if I turn this on, it's drawn the line through the data, and it starts at 0.5 because that's where the intercept is, and the best value of B to get a curve like this is 0.0003. Now, knowing that that is the function of the best fit line, I can just re-put that line in and crop it so that it only shows a curve, a trend line curve for the data in the interval of what we've measured. So basically it doesn't go before 0 and it doesn't go after the final time measurement, 4,500. So there we have a representation of the trend line. Now, what we're going to now do is we're going to identify a point just like this, and I want to see what the gradient is at that point. So what we draw is a tangent at that point. And the cool thing about this is if you type this into Desmos, what you'll do is you'll be able to move the point where you are measuring so that you could work out what the gradient of the tangent is at any point you particularly like. And what you can see is what it's doing is it's telling us the what the gradient of the tangent line is just here. And so I know the rate of reaction, and it's being published down here. And you can see that the rate of reaction is getting less as it gets less steep, and it's getting more as it gets more steep. So this is how you could use Desmos to find the rate of reaction in a simple reaction of sulfuryl chloride decomposing into sulfur dioxide and chlorine. Now, it might be that you don't have access to a fancy graph drawing program, and indeed you won't have that in the exam. So you have to be able to manually work out gradients of tangents. So you can see what I've got here is that this tangent is being displayed. This is for the initial rate of reaction just here. And what I'm having to do is I'm having to look at a change in the y coordinate divided by a change in the x coordinate. So I can see how tall is this triangle right now. Well, it's 0.5 high. And how wide is this triangle? Well, it goes up to 3,300. And so the change in the y divided by the change in the x is telling me the gradient of this big triangle here, which is 1.5 times 10 to the minus 4. Now, in that last example, it was a nice, neat triangle. You might not always have a nice, neat triangle. So you might have to just look at the difference in two particular positions. So 0.38 is over here, and 0.14 is about down here. So they've basically drawn a big triangle on that's about this sort of size, the difference in the y-coordinate divided by the difference in the x-coordinate to work out what the gradient of the tangent line is when the tangent line is drawn at this position of about 3,000 seconds. So now is your chance to put everything you've learnt to action and draw a concentration time graph. Now you could draw it on paper, you could draw it on Desmos, but what I would like to know is what is the initial rate of reaction for this, and also what is the rate of reaction at 50 seconds. You can see that what I can do is, well, I have no data point at 50 seconds, but I can interpolate between the 30 and the 60, and I can work out what the tangent is at a point at 50 seconds. That is the power of these graphs.